So good day class, or less for this about power series using the Matlab software. So let's try to consider first yung topic about the partial sum before proceed to the Maclaurin and Taylor series. So for the partial sum in Matlab, so for infinite series, okay, in this form, a subdivision of a sub k, where k here runs from 1 to infinity. So we define the n partial sum as in this form, no? So we say that the infinite series converges to S if the limit of S sub n as n approaches to infinity is equivalent to this S, no? So example, for given this series, so we're tasked here to compute the partial sum of S10, S10,000, this is 1 million, and this is 10 million, and make a conjecture as to whether or not the series converges, and if it is converges, what's the converges to in value. So we can solve this using the Matlab code. Okay, we define first what is the value of k. So if we want to determine S sub 10, so for the partial sum from k is equals to 1 to 10, so we need to define first what is the value of k. So 1 colon 10. So this will generate the k value 1, 2, 3 up to 10. And using the sum function, so temporarily we can store the sum as S, no? So S equals to sum, okay? So the given series here is in this form, 1 over k, then raise it to 3 over 2. So this will give us a value of 1.9953. So similarly, to determine yung partial sum for S sub 10,000, okay? So we define k value, 1 is to 1 to 10,000, and S equals to the sum of the given uh, term, no? Or for this case, in series. So this will give us a S value as 2.5924. Then next one is, this time the k value is 1 to 1 million. So using the same function sum, this will give us S value of 2.6104. So lastly, so this time we define the k value to 1 up to 10 million. So using the same function sum, this will give us S value 2.6117. Okay, so as you can see, as k value approaches to infinity, the S value converges to a value of 2.61. Okay, so we can state here that this given series is actually a convergent series, no? So another example for this harmonic series, compute the partial sum S10 to S10 million and make again conjecture as to whether or not the series converges, and if it converges, what is the convergence value. So again, we can define the k value 1 to 10. Okay, this time the given harmonic series is 1 over k lang, no? So this gives us a value of 2.9290 for the S10, no? Next S partial sum 10,000. So define the k, this is some function, so give us 9.7876. Okay. Then third one, S 1 million. Okay, just give us S value 14.39. And lastly, S 10 million, just to give us this value. Okay, so as you can see, this is actually a divergent series. Okay, kasi as x approaches infinity, so wala siyang convergent value, no? So iba-iba. So from k value to 1 to 10, 2.92 lang, no? While 10,000, naging 9 na kagad. Then 1 million, naging 14. Then 10 million, this will give us this value. So the concept of Taylor series was discovered by Scottish mathematician James Gregory and formally introduced by the English mathematician Brooke Taylor, okay, in 1715. So this series is based on the Taylor's theorem that states that any smooth function can be approximated in the neighborhood of an expansion point A as in polynomial form. Okay, f of x equals to this expression, where f raised of a is the kth derivative evaluated at x equals to a. So if the Taylor series is centered at 0, so the expansion point A is set of 0, then the series is considered as the Maclaurin series or the power series. So yung formula is ganito, no? F of x equals to this expression. So it should be noted that the Maclaurin series, okay, or as a matter of fact, the Taylor series just centered at any point A of the polynomial function is finite and is identical to the polynomial itself. So recall this, okay? So just to summarize the difference between the Maclaurin and the Taylor series. So example, so find and compare the Taylor series approximation for the given function sine x at a is equals 0. So we define the first derivative, second, third, fourth, fifth derivative of the given function. And of course, we need to evaluate the given function's derivative at x, or for this case, a is equals 0. So just give us the following values, no? First derivative up to the fifth derivative. So which leads us to the following polynomial approximation. Okay, so p sub naught of x is equals to give us 0 value, p sub 1, x na lang, p sub 2, x, p sub 3, x minus x3 over 3 factorial, p sub 4 is the same as p sub 3, and p sub 5 is equivalent to this expression. So the following is the Matlab plot comparing the various p sub n of x approximation of the sine x. So we can define the p sub 1 value as x. So this is the same as we use this at symbol to define our function p sub 1 of x. Okay, so this is the same as you're declaring y as x, no? So similarly, so we can define the function p sub 3 as this form. So p sub 3 equals that sign of x. So we define the function, no? And p sub 5. So y is equals to the same as p sub 5 of x. So this is the polynomial form. And of course, we need to define our x from negative pi to positive pi with the increment of 0.01. So using the plot function, we can plot the given function sine x, p sub 1, p sub 3, and p sub 5. So the same set of the domain x, no? So of course, this green line represent yung p sub 1, okay? Then the red one is the sine x, okay? Then p sub 3 is the magenta, so ito yun, okay? Then last one, p sub 5 is the blue line dito, okay? So note that the higher degree polynomial approximation are closer to the function sine of x over the wide range of x or domain x. Of course, the more terms that we add, the better will be the approximation for the given function. So Matlab has convenient function for generating the Taylor polynomial. So the syntax would be Taylor, then the given function, comma. So we define the variable x, comma, then a here represent yung constant value, comma, then we can also state here yung order, comma, then n. So f is of course our function, x is the independent variable, a is the point at which the expansion is to be performed. So the default value here is 0. And order n is generates an approximation up to including n minus 1 order term. So if the order is not specified, the default value is n is equals to 6 now. So the rotation order of this Taylor series expansion specified as a positive integer or a symbolic positive integer. So Taylor computes the Taylor series approximation in the order of the n minus 1. So the rotation order n is the exponent on the term 0 term, or 0, then yung variable natin raised to n. So example, seems x. So Taylor yung function sine of x. Then let's say here, the order. Okay, that 5. So this will give us this answer now. So we expect here that the highest degree of the polynomial will be up to n minus 1 lang. So for this case, if we define the order as 5, so the highest degree would be 5 minus 1, which is 4. So for this case, if we try to recall, okay, yung expansion ng piece of 5 natin is up to this one lang, no? Kasi the highest degree is 4. So we expect that the expansion will be up to these two terms only. Okay. So another example. So we define the x as symbolic. We define our function as sine x. So using the command Taylor, so the function f, then we define the independent variable x, then state the order. This will give us this term, no? Then another example for this case, we have the value of t. So we define our a as 1, okay, and we state here the same order. So this will give us this expression, okay. So the highest degree would be x raised to n minus 1, which is for this case our n here is 5, so up to 5 minus 1 is 4, okay. So as you expected, so in Taylor series for the polynomial function is the function itself regardless of the expansion point. So as an example, so say we define yung result ng Taylor series as g. So g is equals to Taylor. This is a function. You can define here yung variable x natin, dependent variable, then yung a value which is 0. So this give us this expression. Now, if we change yung constant value from 0 to 1, so using the same function, this will give us this expression. Now, if we try to expand the result, g, this will give us the same expression as if we're evaluating yung given Taylor series function at a is equals to 0. So the following here is the 11th-degree polynomial approximation for the function sine of x. Okay, so since we're after to the up to 11th-degree polynomial, so we need to set the order up to 12, no? So this will give us this expression. Okay, so the highest degree would be x raised to 11. So we can plot this 11th-degree polynomial by first defining it as an anonymous function. So we define our p of x as in this form. Okay, then define our x from negative 2 pi to positive 2 pi with an increment of 0.01. So using the plot command, we can plot here. So of course we define our x, the sine x. Then the second function will be in polynomial form as p of x. Okay, so the blue solid line represent yung sine x, and I think this is green. So the green one represent yung p of x. Alternatively, we can utilize the sim_symbolic command, which converts the symbolic polynomial to coefficient vector representation. Then we can use the polyval command to evaluate the polynomial as follows. So you can change yung format natin as long. So format long. Then again, define our x as symbolic. So temporarily, we can store the output of sim_symbolic as vector p. So p is sim_symbolic Taylor of the sine x. So x, the constant value here, or a value is 0, then set the order to 12. So this will give us this result p. Okay, so we can generate here a column from 1 to 12. Okay, then define our x from negative 2 pi to positive 2 pi with increment of 0.01. Then using the plot command, so this will plot yung function as well as the result ng polyval. We're evaluating here the result ng vector p evaluated at x value from negative 2 pi to positive 2 pi. So this will give us the same result, no? So that's the end of our presentation. So you can answer the given activity about the plotting, okay, by following to the given link shown on the screen. So thank you for listening.